In an industry where just one single stray microbe can ruin a multi-million-dollar batch of medicine, purity isn't just a goal, it's absolutely everything. Today, we're going to explore the invisible war against air-based hazards and see how science protects the medicines that we all rely on. So that brings up a really fascinating challenge, right? The very air we breathe can be a highway for contamination. So how in the world does the pharmaceutical industry engineer solutions to protect its products from this constant, ever-present risk? Well, let's start by getting to know the enemy. All right, to win this war, we first have to understand what we're up against. So let's define exactly what an environmental hazard is and why the air itself is such a huge concern inside a pharmaceutical facility. Okay, so at its core, an environmental hazard is really just anything with the potential to cause harm. Now, what's so important here is that this isn't just about something like a chemical spill. Notice the definition includes a state, like the wrong temperature, or an event, say a power failure. This forces us to take a much broader, more complete view of safety. And this is where we really zoom in. In pharma manufacturing, the air itself acts as the main delivery system, a vector, for all sorts of contaminants. A single little particle or microbe just floating around can compromise an entire batch of medicine, which affects its safety, its stability, and ultimately whether it even works. So what are we actually dealing with here? Well, the threats really fall into two main buckets. On one hand, you've got chemical hazards like benzene, which are often just byproducts of the manufacturing process. But on the other hand, and you could argue these are even trickier, are the microbial contaminants. We're talking bacteria, molds, and viruses, all floating around completely unseen. Both types can be totally devastating to the product. So now that we've laid out the threat, how do we start to manage it? I mean, you can't control what you don't understand, right? That's where the industry uses a systematic approach called a preliminary hazard analysis, or PHA for short. The best way to think about a PHA is like it's the foundational blueprint for safety. It is the very first step you take when you're designing or just evaluating a process. The whole goal is to proactively find and categorize any potential hazard before it can ever become a real problem. The process itself is just beautifully logical. It really breaks down into three core objectives. First, you identify absolutely everything that could possibly go wrong. Then, second, you rank those events. Is it a minor issue or is it a catastrophic failure? And third, based on that ranking, you figure out the specific controls and actions you need to take to shut down that risk. It's a structured way of turning all those what-ifs into a solid, here's how we fix it plan. Identifying risks with a PHA, that's the thinking part. Now let's get to the doing part. The main engineering tool we use to manage the air itself is the HVAC system. Now, in a pharmaceutical setting, HVAC is so much more than just your office air conditioner. It's a high-precision machine. It's designed to take regular old outside air and completely transform it. It cleans it, it controls the temperature and humidity, and then it carefully circulates it through the manufacturing space to create this incredibly controlled environment. And this diagram shows that basic workflow perfectly. You can see the outside air getting pulled into the air handling unit. Once it's inside, it passes through a filter to get all the particles out. Then, depending on what's needed, it's either cooled by the chiller or heated by the boiler before a fan pushes that clean, conditioned air right into the room. It's this continuous loop of purification and control. So here's the crucial point. A really good HVAC system actually serves three different but connected purposes. It protects the product from us and from the outside world. It protects the personnel from the product, which is super important if you're dealing with potent compounds. And it protects the outside environment from anything being made inside. It's a complete safety ecosystem. Okay, so we've got the theory down. But how does this all work in practice? Well, the key thing to get is that not all manufacturing areas are the same. The strategies for managing air are dramatically different when you compare non-sterile and sterile production zones. Now, what's really interesting here is the direct comparison. In a non-sterile area, your main goal is dust control and comfort, so you're going to use standard filters. But in a sterile clean room, oh, that's a whole different world. The goal there is to prevent microbial contamination, period. And that requires a totally different approach. Strictly positive air pressure to literally push contaminants out, incredibly high-efficiency HEPA filters, and a one-way airflow to just sweep any remaining particles away. The difference is truly night and day.
This chart really drives that last point home. Look, on the left, you've got your standard filters, which are designed to catch bigger things like common dust. But over on the right, you have aerosol filters like HEPA and OPA. These are engineered to capture unbelievably small particles, all the way down to submicron levels, which is exactly where bacteria and viruses live. This is the technological leap that makes sterile manufacturing even possible.
So, we've covered the hazard, the analysis, and the control systems. Let's boil all of this down into the core principles you're going to want to remember for your exams and for your future career. All right, for your revision, just lock in these 4 points. Number 1, air is an active threat vector. Gotta manage it. 2, PHA is the strategic process you use to analyze that threat. 3, HVAC is the main engineering tool you use to control it. And 4, the way you use that tool, especially with pressure and filtration, has to be totally different for sterile versus non-sterile areas. And I'll leave you with this to think about. The principles we've talked about are the foundation for today, but this industry is always evolving. As we move into an era of super sensitive and personalized medicines, like cell and gene therapies, how are these fundamental ideas of environmental control going to have to adapt to meet even tougher requirements? That, right there, is the next frontier for pharmaceutical science.